In the last two videos, we've seen that the Runge-Kutta method offers us accuracy and speed if we implement an adaptive step size. So far, we've limited ourselves to working with only first-order differential equations, where we have an expression for the first derivative in terms of the independent variable and the dependent variable. But most applications in physics require solving a second-order differential equation. For example, Newton's second law and the RLC circuit are both unavoidably second order. They give us the second derivative in terms of the independent variable, the dependent variable, and the first derivative. We can extend the Runge-Kutta method to solve a second-order differential equation with just a few simple modifications. In this code, which is available in the description below, we've set our second derivative equal to the negative of the dependent variable, which should give us a sine or cosine. This derivative function now returns a vector that contains the first derivative and the second derivative. When this derivative function is called, the first argument is the independent variable, and the second argument is a vector that includes the dependent variable and the first derivative. Notice that these variables line up with their derivatives above. Finally, after calculating the partial steps as before, we combine them into a weighted average for the steps in the dependent variable and the first derivative. If we run the code, we see that we get a cosine curve as expected. Note that the adaptive step size is still in effect, causing the animation to change speed depending on the needs of the function. Here, we've added a damping term to the second derivative, and the result is a decaying cosine curve. By the way, notice that you can extend this method to higher-order differential equations just by including more derivatives in the vector. For example, to model a third-order differential equation, you would add the second derivative to the z component of this vector. To go higher than third order, you would need to use a list or an array instead of a three-dimensional vector. You should now be able to implement the Runge-Kutta method with an adaptive step size for a given second-order differential equation and a given set of initial conditions. Follow the link in the description below and modify the code to use the Runge-Kutta method to solve these differential equations.